Welcome to Robotics 2. We are going towards the final stretch. So today's class is actually the last class from this textbook, and we are going to work out some drone related topics, explore drone topics, that is quadcopter in next classes. And I'm asking you to watch some webinars that are MATLAB and then actually perform the programming activity in the MATLAB. Once again, please understand next few activities, basically next 3 projects. I would really like if you can do it on your own. That would give you a lot of confidence and understanding. But even if you work in the teams of 2 or 3 or 4, that is totally fine. But at the end, once again, you should fly your drone. So please do not use someone else's drone, create the video. Because remember, for every drone, you need to show the serial number when you take the video. So please follow the honor code. It's okay to work together, help each other, but at the end, you want to fly your drone. So you are welcome to work in the teams. I would really like if you can work alone, but it's okay to work in the teams and help each other. Okay, so chapter 11. In this chapter, we are going to extend the discussion that we started in last class. And we are looking at something called as the path manager. Now, this chapter, just like the previous chapter, talks about some theoretical concepts. But at the end, what happens is it's a simple algorithm that can be implemented inside MATLAB or using Python that would allow you to actually implement these mathematical equations into some type of if then else type of statement. So please understand, so far we actually looked at the MAV dynamics, we looked at the autopilot, we looked at the path following. Now we are at the path manager, and we are going to look at how this structure works. So first and foremost, let's start with the definition of path. Now, what do we mean by path? Please understand, trajectory means you have a path on y-axis and you have a time on the x-axis. But if you are just following path, that means you have waypoint definitions and you want to follow these waypoints from first waypoint to the second waypoint, third waypoint, so on and so forth. Remember, these waypoints need to be defined in the inertial coordinate frame. And our inertial coordinate frame is north, east, and down. And this inertial coordinate frame is fixed. So what we are going to do is we are going to define these path waypoints W1, W2, W3. So this is a W1, W2, W3. And each waypoint would have its Wn, which is the north position in terms of the inertial coordinates, which means basically the distance between the origin and the first waypoint in the north direction, We, which is the east direction, and Wd, which is the down direction. And again, this is considered as a Hilbert space. So as we can see, it's r to the power cube, which means it's a 3-dimensional representation. Now the question is, if I have a UAV that is flying from first waypoint to the second waypoint, when does the UAV turn? Because at some point, you have to follow the straight line, and towards the end of the straight line, you need to make a turn. So how do we decide what point to turn and how to use this path as some type of a guidance? So for that, what we do is there are two methods. The first method is called as b-ball around the waypoint. Now b-ball essentially means that you start with this first waypoint W1 and you go to the second waypoint, and now you want to switch to the third waypoint, so that you want to go from W1 to W2 to W3. So as soon as this UAV reaches this neighborhood of waypoint 2, and this neighborhood of waypoint 2 is considered as a B ball. This is an imaginary ball that is constructed around the waypoint. So what that means is as soon as this UAV reaches this waypoint, it will kind of start turning, and it will continue to turn till it exits the ball. So, and then it will continue to go in the straight line. So this is meaning the B ball. So UAV will continue to advance toward the waypoint. As soon as it reaches the waypoint, as soon as the UAV is close to the waypoint, it turns and it starts traveling in the third waypoint direction. Now, next approach is basically half plane through the waypoint. So what do we mean by half plane? Half plane means you have this waypoint and we actually construct a plane. So you have a plane on the left and you have the plane on the right. So these two planes are divided by this line that is passing through waypoint 2. And as soon as the UAV crosses this half plane through the waypoint, it actually switches. So basically it goes like this. So it goes forward and then it goes like this. So this is something called as the waypoint switching. Now, it's very easy to explain what is happening or what we want to do. The question is, how do we write all this in terms of algorithms? So what type of code that you want to write inside the autopilot wherein this type of switching can happen? And that is where all this math comes in the picture. So what happens is HRN is the plane that is defined by P, which is a Hilbert space R cube. And then we are going to define a vector. And please understand, this vector is nothing but a unit vector. So as you can see, say for an example, if this is point A, this is point B, what we want to do is we want to find out the unit vector that is indicating the direction. That's why you have the actual vector divided by the magnitude of the vector. And then what we do is we construct a unit normal to the 3D half plane, wherein this unit normal is separating this line that is basically the previous line and the next line. So what that means, basically it is separating out these two lines. And then what's going to happen is we find out the unit vector here. And then what we do is we say as soon as the MAV enters this half plane, then it switches and continues to follow straight line path. So this is the mathematical way of representing how this will work. Now, in terms of implementation, what you will have is you can program these waypoint switching. There are different ways of doing it. Say if you use a ground station, something like for the Pickhawk or for Ardu pilot, if you use a ground station, once you actually construct the waypoints, the ground station software automatically will perform these calculations and set up the points for the MAV to track. Now, what does that mean? It means if you want your UAV or MAV to follow this path, based on this logic, the ground station software is going to construct this normal, going to find out the line, and then is going to track, or based on the turning radius of the UAV, it is going to find the series of waypoints that will transition the UAV from approach towards the ball and exit from the ball, or approach towards the half plane and entering in the half plane. Now, this is how the logic is being implemented. So for an example, you have these waypoint path, and many a times what happens is the software or ground station software allows you to add or remove waypoints. So for this algorithm to work, at minimum, you need 3 waypoints if you want to have the straight line motion and turning motion. If you just want a straight line motion, then you need 2 waypoints. But what happens is you have waypoints defined by W1 all the way to Wn. And then you have the position vector P, which is nothing but the component in the north, east, and down direction. And as soon as if you receive a new waypoint, you increment the index of the waypoint, you find the unit vector for the previous waypoint, you find the unit vector for the second waypoint, you find this unit normal that indicates the transition, and then basically perform the maneuver. So this is the mathematical way of representing what we discussed in the last slide. So this would be the waypoint following algorithm. Now, what that means when you are going to perform a simulation, and I want you to notice this. If you use a Pickhawk, or if you use Ardu Pilot, or if you use any other software, it will actually simulate the motion of the UAV. What that means is, if you run simulate the UAV, you will actually see that UAV is tracking certain path. And assuming you start from this point, this is a straight line motion, and you would notice as soon as the UAV tends to enter this particular ball, you are going to have some type of a turning, and clearly the UAVs cannot do a 0-point turn, or for an example, fixed wing UAVs cannot do a 0-point turn, quadcopters can, and then basically you can follow this path. Then it will go to the second waypoint. Here again, there is going to be turn. Then it will follow the third waypoint, and then it's going to go to the turn, and then it's going to go down. And this is where it will stop. So you are starting, this is your start point, and then this is your end point. This is your start point, and this is your end point. Now the next question is, how are we transitioning when we are actually turning? So we have 3 waypoints, W1. We have the second waypoint, W2, and we have the third waypoint, W3. So clearly, the MAV or fixed wing aircraft cannot do super sharp turn. So we need to attach basically some type of smoothing algorithm that would actually add this fillet radii. So what we want to do is we want to add this fillet. Now, what happens is mathematically, you would add this fillet. So you will find the equation of the fillet between these 2 straight lines, and the algorithm will discuss in just a minute. So you will find the equation of the fillet in these straight lines, and then add the waypoints on the fillet that UAV or MAV will track. So that is how MAV will go from previous waypoint to the next waypoint. Now the question is, how do we find out this fillet geometry? And this fillet geometry is, as discussed, it's a simple geometrical equation. So what you have is, think about that you have the radius of the fillet. Think about you have the length or R, which actually is needed to make sure that UAV follows the appropriate turning radius. And then what you have is, you have this angle, which means what is the angle between, say, for an example, this could be 90 degrees. This could be 135 degrees. This could be 110 degrees, etc., etc. So basically, these path parameters can be defined purely using the geometry. And you can use a simple high school geometry. And then once you apply that, you get these path parameters. And then you can find these fillet circles. Now, I want to tell you, I don't know if you use the CAD software like SolidWorks or CATIA or Autodesk Fusion. So there, if you create a solid model, you can actually select two straight lines and then click on the prompt and create a fillet. So the logic or the algorithm that creates the fillet between two intersecting lines is exactly same as this. So this algorithm that is shown over here, which is purely based on the geometry, is the same algorithm that is used by the CAD software to draw a fillet between two straight intersecting lines. And as you can see, those depend upon the angle, and then you can find out the half plane, and then you can find out the second half plane. So basically, you have this first half plane, and you can have this second half plane. Next thing is, if you want to modify the algorithm that we talked about using the fillet. So you're not gonna use the straight transition, but what you're gonna make sure is your UAV or your plane follows the straight line, and then at certain point, it basically transitions using a fillet and then comes down. So if you want to do that, here is the mathematical algorithm that is discussed. And this actually uses something called as the state flow or state machines. So you will have if, else, then type of statements. And depending upon where you are going to transition from different states. So as you can see, first is initialization. Then you find out the unit vector. Then you find out the radius. Find out the angle. Then basically see what state you are in. And then you follow the algorithm which is shown over here. Then you check for the second state. And then if you are in the second state, you actually work on the second part of the algorithm. So this is a straight transition based algorithm, and you can follow that and transition from one path to other path. Now, one thing you will notice that if you were to add fillets to the waypoint following, your transitions are going to be much smoother. So you are going to have transitions that are much smoother and that are shown over here. Now, next part is calculation of the path length. And if you want to find out the straight line path, the straight line path is nothing but this. If you want to find out the straight line path with fillet, you would have an arc in between, and you need to take into account the travel distance within the arc. Now, next part, and this is something very commonly used, and this Dubins path, this is used not only in UAVs, this is commonly used in UGVs, This is also commonly used in warehouse robotics. So you will see this Dubins path. If you take any course in autonomous ground vehicles or autonomous underwater vehicles, this concept of Dubin paths will cross your path. So the idea is, instead of defining path as we defined earlier, what we do is we define the path as the transitions of the states. So in other words, we are going to come up with different configurations, and we'll try to find out the most optimal configuration that is possible. So a simple example is, imagine this is the path. Here we have a left-hand turn, we have a straight line, and then we have a right-hand turn. So this transition is given as LSR. So there are 4 combinations possible. So let's look at a simple vehicle wherein the geometry, based on the geometry and based on the airspeed, we get the values of V cosine theta, V sine theta, and theta dot is equal to U. So what we are going to do is we are going to define this path using some standard configurations, and we are going to list all the possible combinations. So what are the possible combinations of the configuration? So it could be LSR, RLS, and so on and so forth. So we want to look at all those configurations, and then we are going to find out the most optimal configuration. So these are the 4 standard cases for Dubins path. As you can see, if you are going from this point all the way over here, you have R, you have straight line path, and then you have R. So you have R over here, you have S over here, and you have R over here. Then you have R over here, then you have S over here, and then you have L over here. This indicates the right hand rotation. This indicates the left hand rotation. The case number 3 is you have the left hand rotation, then you have the straight line configuration, and then you have the right hand rotation. And then the last case is the left hand rotation, then you have the straight line rotation and motion, and then again the left hand rotation. So now what we are going to do is we are going to use this logic and then see in the configurations that we have, which is the shortest of these 4 potential paths. And then what we do is we use again simple geometry calculations to find out the total path length. And this path length is given as in terms of geometric parameters. Like you have this position, you have the course, which is chi, and radius, and you can find out that the distance it needs to travel either from the right hand turn or from the left hand turn. So basically you got this left hand and right hand turning centers where you have R and L, and you want to find out the total path length. To do the path length, you need to know the radius of the path, or basically the radius of the circle, and you also need to know where the center is. So with this equation, first you are going to find out the center of the circles. Then if you have a circle that is clockwise, then what you're going to do is you are going to use the angular difference between 2, and that is actually expanded as this, depending upon whether you are going clockwise or counterclockwise, and then you get this equation for the total travel. This is nothing but the angular travel. So you can go from like this, or you can go from like this. So there are different ways of going around the circle. Either you can go clockwise or you can go counterclockwise. And depending upon what Dubin path you use, you will have to use the appropriate equation. Alternatively, you can actually express this in terms of moduli. And again, the algorithm is the same, logic is the same. You find out the angles, and for each turn, if you are going left, turn counterclockwise. If you are going right, turn clockwise. So that is what is the thing that needs to be taken care of. And these are the equations here, and this is the equation here. The next part is again same thing. If you are looking at the counterclockwise, you can use the mod type of formulation and get these equations for the angular displacement. So basically, it's gonna give you the angular travel. Then what happens is we can consider the 4 cases that we talked about, RSR, and then that would allow us to calculate the distances. For example, if you have the case where first one is the right hand turn, straight line path, and right hand turn, then you have first, second, and finally you get this equation for the total path. So this would be the first path Dubin case, wherein you have right hand turn, straight, and then right hand turn. So basically you start from this point, take a right hand turn, go straight, come here, and then you get to this point. Next case is if you have the right hand turn, straight, and left hand turn. So please understand, you take a right hand turn here, then you go straight, and you take a left hand turn. So you have the distance traveled around circle, then you have the distance traveled around the second circle, and finally you have the straight line travel, which is given over here. So this is what it is. Then the third case is LSR. So if you travel along LCS or CLS, which means the first circle, then you get this travel distance from here to here. Then if you look at the second, this is the travel distance. And then what you do is you find this. Now here is what's going to happen. Whenever you actually use this Dubins path, once you give the waypoint, the software will automatically calculate the Dubins path. Now what that means is it will tell you that if you want to go from this point to this point, whether you'll be turning like this, or whether you'll be turning like this, or whether you'll be turning like this. So it will actually perform these calculations internally. And out of these 3 cases, it will find out the potential for paths, different path lengths, and then it will give you the appropriate path. So the basic logic is you are going to implement these 4 equations, and then out of that, you are going to choose just the minimum equation. Now, how would you implement this Dubins path if you have a half plane switching? So what you have is you have a start and end configuration. And now what we want to do is we want to find out the path. So you have the start location, you have the start direction, you have the end location, you have the end direction. So this is given. And this Dubin path parameters, you have the start circle location, then you get this start circle direction, you get end circle location, you get end circle direction, and then algorithm will calculate these plane parameters, which is half plane, which is H1, half plane, which is H2, and finally the half plane, which is H3. So once these are calculated, you can see that this algorithm, again, there is a fantastic code in the MATLAB that would actually calculate the Dubins path. And you don't have to write this code, but this is the code or algorithm that is used to find out the Dubin path parameters. And some of you may say, what is the use of it? So at the end of the day, what's going to happen is you will have a particular task to be performed going from point A to point B. And this Dubin path algorithm will actually tell you what would be the best path to follow. And after implementing the algorithm, you would actually have maybe X, Y, and Z's that are along this path. Or you could have the direction cosines and the magnitude that will give you the travel and the orientation. So I would encourage you to take a look at these algorithms for the Dubin path. We don't write these algorithms, but MATLAB, and for that matter, even Python, these algorithms are implemented. And once you implement these different algorithms, you can actually see how the Dubin path planning works. And here is a simple comparison that we are trying to make this type of the shape that is shown over here. So this is the shape that we want to make. And if we were to use the Dubin path type of approach, then by the algorithm, if we were to implement it, this algorithm will give us this potential path. So next thing which I want to tell you is, and again, this is very well explained inside the MATLAB, wherein what needs to happen is, if you have a Dubin path, you can actually use the algorithms which has RRT, or you can use the other path planning algorithms that would actually make this process much more efficient. And we are not going to talk in detail about what algorithms are. There are A star, there is RRT. What I'm going to do is I'm going to give you a link in the modules to a small 10 minutes video, which actually would give you understanding of what these different algorithms are. And you can actually combine these algorithms with Dubin's path. And what that would do is that would allow you to plan the path when you have obstacles. So for example, if you combine RRT type of algorithm and with Dubins, then you will notice that it will generate a very nice path when you have the dense environment. And RRT is nothing but something called as rapidly exploring random trees. I'll just write this down. Rapidly exploring random trees. So, and these are used when you have obstacles or you are performing maneuvers in a contested environment, or you have basically swarms of UAVs. And then what you can do is you can actually come up with search algorithms, and then you can find out the appropriate tree and then find out the best path to follow. And then again, what you have is, if you want to do a Dubin's path with CCC, then as you can see, you have three circles: C1, C2, C3, CE, CM, CS. And then what you do is you find the angles, and then it will give you the cases for RLR and LRL. You can actually extend what we discussed earlier, and you can find out the centers, you can find out the unit vectors, and you can find out the angles and the intersections, and the equations are given in the textbook. But the logic is you would incorporate same logic as Dubin path by looking at looking at adding one more center, which is in between 2 points. Now, if you want to use CCC type of Dubin path, then you have RLR length, which is shown over here, and LRL length, which is shown over here. And then these can be incorporated in your path planning algorithm. Now, this is a simple MATLAB script wherein if you have a UAV and what you want to do is you want to perform the maneuver. And so this is actually shows an example of different types of paths that are calculated by the algorithm. Now, it is very important that the path planning algorithm that you have is robust, which means it's computationally, not only computationally fast, but there are no singularities. And then it is able to do the full path and orbit, because you don't want your formulation to break down in the middle of the flight, or you don't, I mean, you come up with a path, but the autopilot or the control system cannot do it. So that's why robust path planning algorithms are super duper important. And this is actually a great area of research, that how do we come up with different robust plans. And if you are going to become an autonomous car engineer, then path planning is extremely important when you are doing autonomous navigation. And again, what you can do is some of this material, that shaded material, comes from various publications or papers that are written by different authors. But let me tell you, this is an active area of research, and you can do your entire PhD in this. So we, again, if you really want to perform some simulations, I would encourage you to basically read this paper, which actually talks about how do you implement Dubins path for the fixed wing aircraft. And the idea is you have the aircraft kinematic parameters, Rn dot, Re dot, Rd dot, and the change of heading. And you have these commanded values, and these commanded values are given in terms of a flight path angle and the roll angle. And you can actually perform the path planning, adding either the vectorial approach, or you can use the path planning using the topology and geometrical approach. So if you are really interested in path planning, I would encourage you to take a look at this paper, which is written by the authors themselves, which actually uses the Dubin European model for the path. You can actually look at the vector field based navigation or tracking and path following, basically. And again, there are topological based techniques. So you can use these vector techniques, vector based techniques. You can use Dubin path, you can use topological planning. And I would encourage you to take a look at these different algorithms. Again, this is active area of research, and I would actually, this, even though it is a little bit boring, but what I'm gonna do is I'm gonna upload a link to a nice video that actually is sort of a cartoon video that will actually explain the applications of these different paths and path planning algorithms. With that, I'm gonna stop here, and I would be happy to answer any question you may have. But it is extremely important that all of you should start working on assignment 6 and start working out and programming your drone, and then ready with your demo. If for some reason your Mambo is not working, or if your motors failed, or if you have some issue connecting to the hardware, please send me an email and stop by my office, and I will give you the spare Mambos that we have bought. At this point, I'm going to stop recording, and see if there are